In the early decades of the 20th century, astronomers believed they had a pretty good handle on the cosmos. The universe, as far as anyone could tell, was static and eternal. Stars drifted through space, galaxies hung suspended in the cosmic void, and everything remained more or less where it had always been. It was a comforting picture, really. A universe that simply existed, unchanging for all of eternity. But then, in the 1920s, everything changed. A young astronomer working at the Mount Wilson Observatory in California made a series of observations that would completely upend our understanding of reality itself. His name was Edwin Hubble, and what he discovered was so profound, so fundamentally strange, that even Albert Einstein initially refused to believe it. The universe, Hubble found, was not static at all. It was expanding. Every galaxy we could observe was racing away from us, and the farther away a galaxy was, the faster it appeared to be moving. This wasn't just some minor detail about cosmic motion. This was a revelation that demanded we completely reconsider what the universe even is. But here's where things get weird, and I mean genuinely, philosophically weird. If the universe is expanding, what exactly is it expanding into? Think about that for a moment. When we say something is expanding, we usually mean it's growing larger within some pre-existing space. A balloon expands into the air around it. A city expands into the countryside. But the universe, by definition, is everything that exists. All of space, all of matter, all of energy, all of time. There is no outside for it to expand into, because outside is part of the universe. So what does expansion even mean in this context? This is the question that has haunted cosmologists for nearly a century. It's a question that sounds simple but cuts straight to the heart of some of the deepest mysteries in physics. And to understand the answer, or rather, to understand why the question itself might be flawed, we need to go back to the beginning. Back to those observations at Mount Wilson. Back to the moment when humanity first realized that the cosmos was far stranger than we ever imagined. Edwin Hubble was not the first person to suggest that the universe might be expanding. That honor actually belongs to a handful of theoretical physicists who had been playing around with Einstein's equations of general relativity in the years following their publication in 1915. But Hubble was the first to prove it observationally, and in science that makes all the difference. The story actually begins with a woman whose contributions were largely overlooked during her lifetime. Her name was Henrietta Swan Leavitt, and she worked as a human computer at the Harvard College Observatory in the early 1900s. At the time, women were not allowed to operate the telescopes. Instead, they were employed to analyze photographic plates, measuring the brightness and positions of stars captured on glass. It was tedious, meticulous work, but Leavitt was brilliant at it. In 1908, while studying variable stars in the Magellanic Clouds, she noticed something remarkable. There was a specific type of pulsating star called a Cepheid variable, and the rate at which these stars brightened and dimmed was directly related to their intrinsic luminosity. The brighter the star, the longer it took to complete one cycle of pulsation. This was huge. If you know how bright something truly is, and you measure how bright it appears from Earth, you can calculate its distance. Leavitt had discovered the first rung of what astronomers call the cosmic distance ladder, a method for measuring distances to objects far beyond our own galaxy. Hubble seized on this technique. By 1924, he had identified Cepheid variables in the Andromeda Nebula and used Leavitt's period luminosity relationship to calculate its distance. The result was shocking. Andromeda was not a nebula within our own Milky Way galaxy, as most astronomers believed. It was a separate galaxy entirely, located nearly 1,000,000 light-years away. The universe, it turned out, was vastly larger than anyone had imagined. But Hubble didn't stop there. Over the next several years, he measured the distances to dozens of galaxies and compared them to their velocities. The velocities could be determined by examining the light from these galaxies. When an object is moving away from you, the wavelengths of its light get stretched out, shifting toward the red end of the spectrum. This is called redshift, and it's the same principle that makes an ambulance siren sound lower in pitch as it drives away. What Hubble found was a clear pattern. The farther away a galaxy was, the greater its redshift. In other words, the more distant a galaxy, the faster it was receding from us. In 1929, he published his findings, presenting what would come to be known as Hubble's law. The relationship between distance and velocity was linear, described by a simple equation. The velocity of a galaxy equals its distance multiplied by a constant, now called the Hubble constant. This was the observational proof that the universe was expanding. Now, at this point, you might be thinking, okay, so galaxies are moving away from us. Maybe we're just at the center of some kind of cosmic explosion. Maybe the Big Bang happened at a specific point in space, and everything is flying outward from that location. That would certainly be easier to visualize than this whole space itself is expanding business. But that's not what's happening. And this is where we need to talk about Albert Einstein, because his reaction to the discovery of cosmic expansion is one of the most fascinating episodes in the history of science. When Einstein first formulated his general theory of relativity in 1915, he realized that his equations predicted a dynamic universe, one that was either expanding or contracting. But, like everyone else at the time, Einstein believed the universe was static. So he did something rather bold. He modified his equations by adding a new term, which he called the cosmological constant. This term acted like a sort of anti-gravity, a repulsive force that could counterbalance gravitational attraction and keep the universe perfectly balanced and unchanging. It was a purely theoretical fix, inserted for no reason other than to make the math match his preconceived notions. But even before Hubble's observations, a few physicists had been questioning whether this static universe made sense. In 1922, a Russian mathematician named Alexander Friedmann derived a set of solutions to Einstein's equations that described an expanding universe. Then, in 1927, a Belgian priest and physicist named Georges Lemaitre independently came to the same conclusion. Lemaitre went even further, proposing that if the universe was expanding now, it must have been smaller in the past. Extrapolate backward far enough, and you arrive at a moment when everything was compressed into an infinitely dense point. He called it the primeval atom. We call it the Big Bang. Einstein was not impressed. When he met Lemaitre at a conference, he reportedly told him that while his mathematics were correct, his physics was abominable. But then came Hubble's data. Real, observational evidence that galaxies were indeed receding. Suddenly, the expanding universe wasn't just a theoretical curiosity. It was reality. Einstein had to concede. He later called the cosmological constant his biggest blunder. Although, as we'll see much later in this story, that blunder would come back in a big way. The equations that describe the expanding universe are known as the Friedmann equations, named after that Russian mathematician. They're derived directly from general relativity, and they tell us how the scale factor of the universe, basically how much space has stretched, changes over time. The equations take into account the density of matter, the density of radiation, the curvature of space, and, yes, the cosmological constant, which Einstein tried to delete, but which modern cosmology has resurrected in the form of dark energy. These equations are elegant, but they're also profoundly strange. They describe a universe where space itself is dynamic, where distances between objects can grow not because the objects are moving, but because the fabric of space between them is stretching. It's like if you drew two dots on a deflated balloon, then inflated it. The dots move apart, but they haven't actually traveled across the surface. The surface itself has expanded. So how do we actually measure this expansion? How do we know that Hubble was right, and that the universe is truly growing larger? Well, modern cosmology has developed an entire toolkit of techniques, a cosmic distance ladder that allows us to measure distances and velocities across mind-boggling scales. The first few rungs of this ladder are relatively straightforward. For nearby stars, we can use parallax, the apparent shift in position when viewed from different points in Earth's orbit around the Sun. It's the same effect you see when you close one eye and then the other, and objects appear to jump. For stars within a few thousand light-years, parallax works beautifully. Beyond that, we turn to Leavitt's Cepheid variables and other types of standard candles, objects whose true brightness we know. If we know how bright something really is, and we measure how bright it appears, simple geometry gives us the distance. For even more distant objects, we use type Ia supernovae. These are exploding white dwarf stars, and they're incredibly useful because they all explode with roughly the same intrinsic brightness. They're among the brightest events in the universe, visible across billions of light-years, which makes them perfect for mapping the large-scale structure of the cosmos. Then there are techniques like the Tully-Fisher relation, which connects a galaxy's rotation speed to its luminosity, and the surface brightness fluctuations method, and baryon acoustic oscillations, which are like fossilized sound waves from the early universe imprinted in the distribution of galaxies. Each method has its own range of applicability, its own sources of error, its own systematic uncertainties. And this is where things get interesting, because when we use these different methods to measure the Hubble constant, the rate at which the universe is expanding, we don't always get the same answer. The Hubble constant is usually expressed in units of kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years, so what this tells us is how much faster a galaxy is receding for every additional megaparsec of distance. If the Hubble constant is 70, then a galaxy 1 megaparsec away is moving at 70 kilometers per second. A galaxy 2 megaparsecs away is moving at 140 kilometers per second, and so on. Now, when we measure the Hubble constant using observations of the cosmic microwave background, the afterglow of the Big Bang, we get a value of about 67 kilometers per second per megaparsec. This measurement comes from satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft, which mapped the temperature fluctuations in this ancient light with exquisite precision. But when we measure the Hubble constant using local observations, things like Cepheid variables and type Ia supernovae in relatively nearby galaxies, we get a different value, about 73 kilometers per second per megaparsec. That might not sound like a huge difference, but in cosmology, it's massive. These two measurements disagree by way more than their stated uncertainties allow. This is what's known as the Hubble tension, and it's one of the biggest open problems in modern cosmology. Either one of our measurement methods is subtly wrong in a way we don't understand, Or there's something fundamentally incomplete about our model of the universe. Maybe dark energy isn't constant but changes over time. Maybe there are additional particles or fields we haven't discovered yet. Maybe general relativity itself needs to be modified. We don't know. What we do know is that the universe is expanding, and has been for about 13.8 billion years. But that just brings us back to the original question. Expanding into what? Here's where I need to level with you about something. Every analogy we use to visualize cosmic expansion is, in some way, misleading. The balloon analogy I mentioned earlier, where galaxies are like dots on an inflating balloon, is probably the most common one. And it works, up to a point. It helps you understand that galaxies can move apart without actually traveling through space. That expansion is about the space between them growing. But the balloon analogy has a fatal flaw. A balloon expands into the room around it. There's an inside and an outside. If you're an ant crawling on the surface of the balloon, you live in a two-dimensional world, the curved surface, but that surface is embedded in a three-dimensional space. And that's exactly the wrong picture for our universe. Our universe is not embedded in some higher dimensional space, at least not in any way that matters for understanding expansion. When cosmologists talk about the universe expanding, they're not saying it's growing into some pre-existing void. They're saying that the distances between objects are increasing. That's it. There's no outside. There's no container. The universe is not like a balloon inflating into a room. It's more like, well, it's like itself. There's no perfect analogy because there's nothing else in our everyday experience that behaves this way. But let me try another one. The raisin bread analogy. Imagine you're baking a loaf of raisin bread. As the dough rises, the raisins move apart from each other. If you're a tiny creature living on one of those raisins, you'd see all the other raisins moving away from you. And here's the key part. Every raisin would see the same thing. There's no special center to the expansion. Every point in the bread is moving away from every other point. Now, you might ask, what about the bread itself? Isn't the loaf of bread expanding into the oven? Yes, if you're observing from outside the bread. But imagine you're not outside. Imagine the bread is all that exists. There is no oven, there is no kitchen. There is only the dough, extending infinitely in all directions, and it's all rising simultaneously. That's closer to what's happening with the universe. The fabric of space, if we want to use that metaphor, is stretching everywhere at once. But there's no outside the fabric, because outside doesn't exist. This is genuinely hard to wrap your mind around. Our brains evolved to navigate a three-dimensional world of medium-sized objects moving at medium speeds. We did not evolve to intuitively understand the behavior of the cosmos at the largest scales. So when I say there's no outside, and you find yourself thinking, but there has to be something, that's not a failure of imagination on your part. That's your brain doing exactly what it's supposed to do, applying the rules that work in everyday life. The problem is, the universe doesn't play by those rules. What happened when I started to really understand this, and I mean really grapple with it, was a sort of conceptual vertigo. Because we're so used to thinking of space as a container, a stage on which events unfold. But general relativity tells us that space is dynamic. It's a participant. It can bend, stretch, ripple, even tear under the right conditions. And when we talk about the expansion of the universe, we're talking about a change in the metric, the mathematical description of distances and intervals. The metric is expanding, and that expansion doesn't require anything to expand into. One way to make this more concrete is to talk about how cosmologists actually describe expansion mathematically. They use something called co-moving coordinates. Imagine you assign every galaxy a set of coordinates, like latitude and longitude on Earth, but in 3 dimensions. These coordinates don't change as the universe expands. The galaxies keep their same coordinates. What changes is the metric, the rule for calculating distances between those coordinates. It's like if you had a map where 1 centimeter represented 1 kilometer, and then suddenly 1 centimeter represented 2 kilometers. The positions on the map haven't changed, but the actual distances they represent have doubled. This is called the scale factor, and it's the key variable in the Friedmann equations. The scale factor tells us how much the universe has stretched since some reference time, usually taken to be either the Big Bang or the present day. If the scale factor doubles, then every distance in the universe doubles. Simple as that. This framework allows cosmologists to describe the history and future of the universe without ever having to invoke an outside. We can talk about how the scale factor has changed over time, how it was smaller in the past and is larger now, and will be even larger in the future. We can calculate what the universe looked like 1 second after the Big Bang, or what it will look like 1 trillion years from now, and none of that requires any reference to what the universe is expanding into. But here's the thing. Even though the math doesn't require an outside, our intuition keeps demanding one. We keep asking, okay, but where is all this new space coming from? And that question, while understandable, is based on a misunderstanding of what space is. Space is not a substance. It's not made of anything. It's a relationship between events and objects. And when we say space is expanding, we're saying that those relationships are changing. The distance between 2 galaxies today is larger than the distance between those same 2 galaxies yesterday, even though neither galaxy has moved through space. This leads to some genuinely strange consequences. For one thing, distant galaxies can recede from us faster than the speed of light. And yes, I know, you've probably heard that nothing can move faster than light. But that's not quite right. The rule is that nothing can move through space faster than light. But space itself can expand as fast as it wants. General relativity has no speed limit on the expansion of space. In fact, sufficiently distant galaxies are receding from us at speeds that exceed the speed of light right now. And this brings us to something called the cosmological horizon, or the edge of the observable universe. Because if distant galaxies are receding faster than light, their light can never reach us. There's a boundary about 46.5 billion light-years away, beyond which we can never receive any information. Not because there's nothing there, but because the expansion of space carries it away faster than light can bridge the gap. Wait, you might be thinking, 46.5 billion light-years? But I thought the universe was only 13.8 billion years old. How can we see objects that are farther away than light could have traveled in the age of the universe? And the answer is expansion. When the light from those distant galaxies was emitted, they were much closer to us. But during the time the light has been traveling toward us, space has been stretching, carrying those galaxies farther and farther away. By the time the light reaches us, the galaxy is now 46.5 billion light-years away, even though the light only traveled for 13.8 billion years. This observable universe, this sphere with a radius of 46.5 billion light-years centered on Earth, is not the entire universe. It's just the part we can see, the part from which light has had time to reach us since the Big Bang. Beyond that horizon, there's presumably more universe, maybe infinitely more. We just can't see it, and we never will. And if you're asking, what's beyond the observable universe? Well, more universe, more galaxies, more stars, more space, governed by the same laws of physics. But is that universe also expanding? Yes. Is it expanding into something? No. We're back where we started. The balloon analogy is everywhere. You've probably seen it in science documentaries, textbooks, museum exhibits. Take a balloon, draw some dots on it with a marker to represent galaxies, then blow it up. As the balloon inflates, the dots move apart. None of the dots are special. Every dot sees all the other dots receding. It's a beautiful demonstration of how cosmic expansion works without requiring any galaxy to be at the center. But here's the problem. The balloon is expanding into the room. There's air inside the balloon pushing outward. There's space outside the balloon into which the rubber stretches. If you are a two-dimensional being living on the surface of that balloon, your entire universe is that curved two-dimensional surface. But that surface is embedded in three-dimensional space. The balloon exists within a larger arena. And that's exactly what the universe does not do. Our three-dimensional universe is not embedded in some four-dimensional space in any meaningful sense. At least, not in a way that has anything to do with expansion. When physicists talk about extra dimensions, which they sometimes do in string theory and other speculative frameworks, those are different kinds of dimensions. They're either compactified, curled up so small we can't detect them, or they're mathematical abstractions that don't correspond to physical space you could point to. The expansion of our universe does not involve it growing into some vast four-dimensional room. So let's be clear about what expansion actually means. It means that the proper distance between objects that are not gravitationally bound to each other is increasing over time. Proper distance is the distance you would measure if you could somehow freeze time and stretch a measuring tape between two galaxies. That distance is getting bigger. Not because the galaxies are flying through space, but because space itself, the thing we measure distances through, is stretching. Think of it this way. Imagine you and a friend are standing on an infinitely large rubber sheet. The sheet represents space. You each stand still, not moving your feet at all. But someone starts stretching the rubber sheet in all directions simultaneously. The distance between you and your friend increases, even though neither of you took a single step. Now, get rid of the someone doing the stretching. There's no external agent. The rubber sheet just has this property that it expands over time according to certain equations. And also, get rid of anything beneath or around the rubber sheet. The sheet is all there is. It's not resting on anything. It's not floating in anything. It just exists, and it's expanding. That's the universe. No external space required. The raisin bread analogy gets us a bit closer to the truth, but it still has issues. Imagine an infinite loaf of raisin bread baking in an oven. As the dough rises, every raisin moves away from every other raisin. If you're sitting on one raisin, all the other raisins appear to be moving away from you. The farther away a raisin is, the faster it recedes, because there's more dough between you to expand. This captures Hubble's law quite nicely. But again, we have this problem of the oven. In the analogy, the bread is expanding into the oven cavity. The oven provides the external space. But we need to imagine an infinite loaf of bread with no oven. The dough extends forever in all directions. There is no edge to the bread. There is no space outside the bread. The bread is all that exists. And now imagine that this infinite expanse of dough is rising, expanding, with every part of it moving away from every other part. That's a bit closer to what's happening with the universe. But even this breaks down because bread dough is made of atoms, which are made of particles, and we can ask what's between the particles. Space, on the other hand, isn't made of anything. It's not a substance that can be subdivided. It's a geometric structure, a set of relationships between events. When space expands, we're not saying that some substance is being stretched thin like taffy. We're saying that the metric, the mathematical object that tells us how to calculate distances and time intervals, is changing. The metric is expanding. Let me try to make this more concrete. In flat, non-expanding space, if you want to know the distance between 2 points, you use the Pythagorean theorem. If you move a certain distance in the x direction, a certain distance in the y direction, and a certain distance in the z direction, the total distance is the square root of the sum of the squares. That's the metric of flat space, and it's been drilled into your head since high school geometry. But in an expanding universe, we multiply the spatial part of this by the scale factor. The scale factor is a function of time, let's call it A, that tells us how much larger the universe is now compared to some reference time. If the scale factor is 2, the universe has doubled in size. If it's 3, it's tripled. And this scale factor appears directly in the metric. When you calculate distances, you multiply by A. And because A is changing over time, the distances are changing over time. That's expansion. Nothing is moving into anything. The rule for measuring distances is changing. That's it. Now, you might be thinking, okay, but what determines how the scale factor changes? What makes it increase rather than stay constant or decrease? And that's where the Friedmann equations come in. These equations, derived from Einstein's general relativity, tell us how the scale factor evolves based on the contents of the universe. If the universe is full of matter, the gravitational attraction of that matter tends to slow down the expansion. If the universe is full of radiation, that has a similar but even stronger braking effect. And if the universe has a cosmological constant, what we now call dark energy, that acts like a repulsive force that accelerates the expansion. The balance between these components determines the fate of the universe. For most of cosmic history, matter dominated, and the expansion was gradually slowing down. But about 5 billion years ago, something changed. The universe had expanded enough that the density of matter had dropped, while the density of dark energy, which doesn't dilute as space expands, remained constant. Dark energy took over, and the expansion started accelerating. Today, we live in a universe that's not just expanding, but expanding faster and faster. We'll come back to dark energy later because it opens up a whole new set of bizarre questions. But for now, the key point is this. The expansion of the universe is described entirely by how the scale factor changes over time, and that's determined by general relativity and the energy content of the universe. No external space needed. Let's talk about what we actually observe when we look at distant galaxies, because this gets to the heart of what expansion really means. When we look at a galaxy that's, say, 1 billion light-years away, we're seeing light that left that galaxy 1 billion years ago. We're looking into the past. And when we analyze that light, we see that its wavelength has been stretched. The spectrum of the galaxy is shifted toward the red, longer wavelengths. This is cosmological redshift, and it's our primary evidence for expansion. Now, You might have learned about redshift as a Doppler effect. When a police car drives away from you, its siren sounds lower in pitch because the sound waves are stretched out. Similarly, when a galaxy moves away from you, its light waves are stretched out, shifting toward the red end of the spectrum. That's the Doppler explanation, and it's not wrong exactly, but it's not quite right either. The redshift we observe from distant galaxies is not primarily due to their motion through space. It's due to the expansion of space itself. The light waves are being stretched as space expands during their journey to us. Think of it this way. A photon leaves a distant galaxy and begins traveling through space toward Earth. As it travels, space is expanding. The photon isn't being stretched because the galaxy is moving away. It's being stretched because space itself is stretching, and the photon is embedded in that space. By the time the photon reaches us, its wavelength has increased by the same factor that the universe has expanded during its journey. If the universe doubled in size while the photon was in transit, the wavelength of the photon also doubled. This is why cosmological redshift is different from Doppler shift. Doppler shift depends on the velocity of the source relative to the observer at the moment of emission. Cosmological redshift depends on the integrated expansion of space between emission and observation. For nearby galaxies, the distinction doesn't matter much, but for very distant galaxies, it matters a lot. In fact, for the most distant galaxies we can observe, the ones whose light has been traveling for more than 13 billion years, the redshift is so large that wavelengths have been stretched by factors of 10 or more. Ultraviolet light emitted by hot stars has been redshifted all the way into the infrared. These galaxies are receding from us at apparent speeds that exceed the speed of light. And that's fine. That doesn't violate relativity, because they're not moving through space faster than light. Space between us and them is expanding faster than light can bridge the gap. This brings us to one of the most counterintuitive aspects of cosmology, the difference between the distance light has traveled and the current distance to the object that emitted the light. When we say a galaxy is 13 billion light-years away, we might mean one of two things. We might mean that the light from that galaxy has been traveling for 13 billion years. Or we might mean that the galaxy is currently, right now, 13 billion light-years away. These are not the same. Because space has been expanding the whole time the light was traveling, the galaxy has been moving away from us. By the time the light reaches us, the galaxy is much farther away than it was when the light was emitted. In fact, the most distant objects we can observe, the ones at the edge of the observable universe, emitted their light when they were only about 40 million light-years away from us. But that light has been traveling for over 13 billion years, and during that time, the universe has expanded by a factor of about 11. So today, right now, those objects are more than 46 billion light-years away. This is why the observable universe has a radius of 46.5 billion light-years, even though the universe is only 13.8 billion years old. Expansion stretched the distances during the light travel time. One of the most profound implications of cosmic expansion is the existence of a cosmological horizon. There are galaxies out there, right now, that we will never be able to see. Not because they don't exist, not because they're too faint, but because the light from them will never reach us. The expansion of space is carrying them away faster than their light can catch up. Imagine you're trying to swim upstream in a river. If the current is flowing at 5 kilometers per hour and you can swim at 3 kilometers per hour, you're going to be swept downstream no matter how hard you swim. you'll never make progress. Light from sufficiently distant galaxies is in the same situation. The light is trying to reach us, traveling at the speed of light. But space is expanding so fast that the light is being swept away faster than it can make progress toward us. This defines a boundary, the cosmological event horizon. Any galaxy beyond this horizon is causally disconnected from us. We can never receive any signal from it, and it can never receive any signal from us. The location of this horizon depends on the expansion rate and the acceleration of the expansion. In our universe, with its specific mix of matter and dark energy, the event horizon is currently about 16 billion light-years away in co-moving distance. Galaxies that are farther than this right now will never be observable in the future. No matter how long we wait, their light will never reach us. But wait, you might say, doesn't that mean there's an edge to the universe? Not exactly. The horizon is the edge of the observable universe, the part we can see. But there's no reason to think the universe itself stops there. Beyond our horizon, there are presumably more galaxies, more stars, more planets, all governed by the same laws of physics. We just can't see them. And here's the kicker. Every galaxy has its own horizon. From the perspective of a galaxy 15 billion light-years away from us, there's a whole different sphere of observability centered on them. They can see galaxies we can't, and we can see galaxies they can't. The universe, as far as we can tell, extends far beyond what any one observer can see. It might even be infinite. And if it is infinite, then asking what it's expanding into is truly meaningless, because infinity doesn't need external space to grow into. An infinite universe that doubles in size is still infinite. But is the universe actually infinite? We don't know. And to answer that question, we need to talk about the geometry and curvature of space. Einstein's general relativity tells us that space can be curved. We're used to thinking of space as flat, with parallel lines staying parallel forever, and the angles of a triangle adding up to exactly 180 degrees. But that's only true in flat space. If space is curved, the rules change. There are three possibilities for the overall geometry of the universe, assuming it's homogeneous and isotropic, meaning it looks the same everywhere and in all directions on large scales. First, the universe could be flat. This is the Euclidean geometry you learned in school. Parallel lines never meet. The angles of a triangle sum to 180 degrees, and the universe extends infinitely in all directions. Second, the universe could have positive curvature. This is like the surface of a sphere. If you draw a triangle on the surface of a sphere, the angles add up to more than 180 degrees. Parallel lines eventually converge. And here's the key thing. A positively curved universe is finite in volume. If you traveled far enough in a straight line, you would eventually come back to where you started, like circumnavigating the Earth. Third, the universe could have negative curvature. This is like the surface of a saddle. The angles of a triangle add up to less than 180 degrees. Parallel lines diverge, and a negatively curved universe is infinite. So, which is it? Well, we can measure the curvature of the universe by looking at the cosmic microwave background, that faint afterglow of the Big Bang. The CMB has tiny temperature fluctuations, hot spots and cold spots imprinted on the sky. The typical size of these hot and cold spots depends on the curvature of space. If space is flat, the spots have one characteristic size. If space is positively curved, they appear larger. If negatively curved, smaller. The Wilkinson Microwave Anisotropy Probe and the Planck satellite measured these fluctuations with incredible precision. And the answer is, as far as we can tell, the universe is flat. Not perfectly flat, measurements always have some uncertainty, but flat to within about 0.4%. This is both reassuring and puzzling. It's reassuring because flat space is mathematically simpler, but it's puzzling because flatness is unstable. If the universe started out even slightly curved, that curvature would have grown over time. The fact that the universe is so close to flat today suggests it must have been extraordinarily, almost impossibly flat in the early universe. This is called the flatness problem, and it's one of the motivations for cosmic inflation, a brief period of exponential expansion in the first fraction of a second after the Big Bang. Inflation would have stretched space so much that any initial curvature was flattened out, like blowing up a balloon until its surface looks perfectly flat on small scales. We'll come back to inflation later. For now, the key point is this: the universe appears to be flat, which means it's almost certainly infinite in extent. And if it's infinite, then it was always infinite. The Big Bang didn't happen at a point. It happened everywhere, throughout all of infinite space, simultaneously. Infinite space that was infinitely dense and infinitely hot, and then expanded, becoming less dense and cooler, but still infinite. That's a genuinely hard concept to wrap your mind around. An infinite universe doesn't expand into anything because it's already infinite. It just becomes less dense. But there's a twist. Even if the universe is flat, meaning locally flat on the largest scales we can measure, it could still have interesting global topology. Topology is the study of shapes and spaces in terms of their connectivity and structure, independent of their exact geometry. Here's an analogy. A flat sheet of paper and the surface of a cylinder are both locally flat. If you're an ant crawling on either one, your immediate surroundings look the same, but globally they're different. The sheet of paper extends infinitely in two directions. The cylinder wraps around on itself in one direction. You could walk in a straight line and eventually return to your starting point. The universe could be the same way. It could be locally flat, satisfying all our measurements, but globally it could be finite and wrap around on itself. One possibility is a three-dimensional torus, like a donut but in 3 dimensions. Imagine a cube where opposite faces are connected. If you exit through the right face, you re-enter through the left face. Exit through the top. Re-enter through the bottom. This is called a 3 torus, and it's finite in volume but has no boundary. You could travel forever in a straight line and never hit an edge, but you'd eventually loop back to where you started. Another possibility is something called the Poincare dodecahedral space, where space has the shape of a dodecahedron, a 12-sided polyhedron, with opposite faces identified in a particular way. There are dozens of other possible topologies, each with its own quirks. If the universe has one of these non-trivial topologies, we might be able to detect it. If space wraps around on itself, we might see the same galaxies or galaxy clusters repeated in different directions in the sky. We'd be looking at the same objects from different angles, like seeing multiple images of yourself in a hall of mirrors. Astronomers have searched for these repeating patterns in the distribution of galaxies and in the cosmic microwave background. So far, they haven't found anything. If the universe does wrap around, it does so on scales larger than the observable universe, at least 90 billion light-years across. We may never know. But the point is, even in a universe with non-trivial topology, with finite volume and no edges, Expansion still doesn't require external space. The universe doesn't expand into anything. The volume increases. Distances between objects grow, but there's no outside. A torus that doubles in size is still a torus. It's just bigger. The bigger is measured intrinsically, from within, by comparing distances between points inside the space. No external reference frame is needed. Let me try one more angle on this because I know it's slippery. Forget about space for a moment. Think about time. Time is one-dimensional. It has a direction, past to future, but it doesn't exist in anything. Time doesn't unfold within some larger temporal arena. It just is. Events happen, one after another, and we measure the intervals between them. The geometry of time, if you want to call it that, is just the structure of those intervals. Space is similar. It's the structure of spatial intervals, the distances between objects. When we say space is expanding, we mean that those intervals are increasing. But space doesn't exist in some higher dimensional container any more than time unfolds in some metatime. Space is the thing itself, the relationships, the distances, the geometry, and those relationships can change without needing an external stage. Now, I realize this is deeply unsatisfying to some part of your brain. We want there to be an outside. We want to be able to zoom out and see the universe from the outside, like looking at a globe. But we can't. Not because of technological limitations, but because there is no outside. The universe is not an object within space. It is space. And when cosmologists say it's expanding, they mean the internal geometry is changing. That's the only sense in which expansion is meaningful. So when you ask, what is the universe expanding into? You're asking a question that doesn't have an answer because it's based on a faulty premise. It's like asking, what's north of the North Pole? The question seems reasonable until you understand the geometry of the Earth's surface. Then you realize the question itself is malformed. There is no north of the North Pole because north is defined by the direction toward the pole. At the pole itself, the concept breaks down. Similarly, outside the universe is not a place. It's not a thing. The universe is all of space, and space is expanding, and that's the whole story. So we've established that the universe is expanding, and that this expansion doesn't require any external space to expand into. But that still leaves us with some pretty fundamental questions about what the universe actually is. What is its shape? What is its size? Is it finite or infinite? And what does any of this have to do with expansion? To answer these questions, we need to dive deeper into the geometry and topology of the universe, and explore what our observations tell us about the cosmos on the largest possible scales. Let's start with a simple question that turns out to have a surprisingly complex answer. Does the universe have an edge? Your intuition probably says yes. After all, every object you've ever encountered has boundaries. Your house has walls. Your city has limits. Even the Earth, despite being round, has a surface beyond which there's just empty space. But the universe might not work that way. There are essentially two possibilities. Either the universe is infinite, extending forever in all directions with no boundary, or it's finite but boundless, meaning it has a limited volume but no edge. Both options are perfectly consistent with general relativity, and both are deeply weird in their own ways. The infinite universe is perhaps easier to grasp conceptually, even if it's impossible to truly visualize. Imagine space just going on forever. No matter how far you travel, there's always more space ahead of you, more galaxies, more stars, more of everything, extending infinitely in all directions. If this is the case, then the universe was always infinite, even at the moment of the Big Bang. That might sound contradictory. How can something infinite have a beginning? But remember, the Big Bang wasn't an explosion at a point. It was a moment when all of space, infinite space, was in an extremely hot and dense state. Then space expanded, or more accurately, the scale factor increased, making the average density lower. An infinite universe that becomes less dense is still infinite. It doesn't need to grow into anything because infinity plus infinity is still infinity. The concept breaks our usual intuitions about beginnings and endings, but mathematically it works perfectly fine. The alternative is a finite universe with no boundaries. This sounds contradictory at first. How can something be finite but have no edge? The answer lies in curvature and topology. Let's go back to that sphere analogy for a moment. The surface of a sphere is finite. It has a definite area, but it has no boundary, no edge. If you're a two-dimensional being confined to the surface of a sphere, you can travel forever in any direction and never hit a wall. You'll just eventually loop back to where you started. The surface is finite but unbounded. Our three-dimensional universe could be the same way. It could have positive curvature, like the three-dimensional analog of a sphere, which mathematicians call a three-sphere. A three-sphere is fiendishly difficult to visualize because it requires 4 spatial dimensions to picture properly, and we only have access to 3. But mathematically, it's well defined. It's a space where if you travel far enough in any direction, you eventually return to your starting point. The total volume is finite, but there are no edges, no boundaries, no place where space just stops. If you're thinking this sounds like science fiction, well, yes, but it's science fiction that's grounded in rigorous mathematics and consistent with everything we know about general relativity. The question is whether our universe actually has this shape, and to answer that, we need to measure the curvature of space. As I mentioned in the previous section, the cosmic microwave background gives us a way to do this. By looking at the size and distribution of temperature fluctuations in this ancient light, we can infer the curvature of the space through which that light has traveled. The measurements from Planck and other satellites tell us that the universe is flat, or at least very close to flat, to within about 0.4%. If the universe does have curvature, it's so slight that we can't detect it with current technology. Now, what does flat mean in this context? It means that on large scales, space obeys the rules of Euclidean geometry. Parallel lines stay parallel. The angles of a triangle add up to 180 degrees. The circumference of a circle is exactly 2 pi times its radius. All the geometry you learned in high school applies, and, crucially, a flat universe is infinite. If space is flat and extends in all directions following Euclidean rules, it goes on forever. There's no way to have a finite flat space without introducing boundaries, and we don't observe any boundaries. So, the simplest interpretation of a flat universe is that it's infinite. But here's where topology throws us a curveball. Even in a flat universe, space could wrap around on itself in strange ways. The local geometry could be flat, but the global structure could be exotic. To understand this, think about a video game, specifically an old-fashioned two-dimensional game like Asteroids or Pac-Man. In Pac-Man, when you go off the right edge of the screen, you reappear on the left edge. Go off the top, you reappear at the bottom. Locally, the screen is flat. The geometry obeys Euclidean rules. But globally, the space wraps around. It's topologically a torus, a donut shape. The screen is actually finite, even though you never hit a wall. You can wander forever and keep discovering new pellets, but eventually you'll loop back to where you started. The universe could work the same way. It could be locally flat, satisfying all our curvature measurements, but globally have a non-trivial topology. A 3 torus is one possibility. Imagine a cube where if you exit through the right face, you immediately enter through the left face at the corresponding point. Exit through the top, enter through the bottom. Exit through the front, enter through the back. This creates a finite 3-dimensional space with no boundaries. You could travel in a straight line forever and never hit an edge, but you'd eventually return to your starting location from the opposite direction. This isn't just mathematical abstraction. If the universe had this kind of topology, there would be observable consequences. You'd see repeating patterns in the large-scale structure of the universe. The same clusters of galaxies would appear multiple times in different parts of the sky, like reflections in a hall of mirrors. You'd be looking at the same objects from different angles. Astronomers have searched for these repeating patterns. They've looked at the distribution of galaxies, trying to find matching arrangements that would indicate we're seeing the same structures from multiple viewpoints. They've analyzed the cosmic microwave background, looking for correlated circles that would appear if our observable universe were large enough that we could see light that had traveled more than once around the cosmos. So far, nothing. If the universe does have a non-trivial topology, the scale is larger than our observable universe. The distance you'd have to travel before looping back is more than 90 billion light-years, which is larger than the diameter of the observable universe. We might live in a giant cosmic Pac-Man game, but if so, the game board is so large we can't see the edges wrapping around. There are other possible topologies, some much stranger than a simple torus. One of the more famous is the Poincare dodecahedral space. Imagine a dodecahedron, a 12-sided solid where each face is a regular pentagon. Now imagine that opposite faces are identified, meaning if you exit through one face, you re-enter through the opposite face, but with a twist. The matching faces are rotated relative to each other by 36 degrees. This creates a finite space with spherical geometry. In 2003, a group of cosmologists claimed they might have found evidence for this topology in the cosmic microwave background data from the WMAP satellite. The CMB seemed to show a suppression of large-scale fluctuations, which could be explained if the universe were finite and had this dodecahedral shape. The idea generated a lot of excitement and quite a bit of controversy. Follow-up studies with better data from Planck found no strong evidence for the dodecahedral topology. The suppression of large-scale fluctuations could be explained by statistical fluctuations, cosmic variance, or systematic effects in the data. The dodecahedral universe isn't ruled out, but it's not supported by the data either. It remains an intriguing possibility, but no more than that. The point of bringing up all these exotic topologies is to show that even in a flat universe, which seems infinite, there are ways for space to be finite without having boundaries. And, crucially, in all these scenarios, expansion works the same way. Whether the universe is an infinite flat expanse, or a finite 3 torus, or a dodecahedral, space expansion means the scale factor increases. Distances between objects grow. Galaxies recede from each other. But none of this requires external space. A torus that doubles in size is still a torus, just with larger dimensions measured intrinsically from within. So, when we ask what the universe is expanding into, the answer is still nothing. Regardless of whether the universe is infinite or finite, flat or curved, topologically trivial or exotic. The expansion is a change in the internal geometry. That's it. Let's consider the implications of living in an infinite versus a finite universe, because they're actually quite different, philosophically and practically. If the universe is infinite, then there's an infinite amount of stuff, an infinite number of galaxies, an infinite number of stars, an infinite number of planets. And if the arrangement of matter is random, or even just subject to quantum fluctuations, then somewhere out there, infinitely far away, there's another galaxy exactly like the Milky Way, another solar system exactly like ours, another Earth with another version of you listening to another version of this documentary. In fact, there are infinitely many such copies. This is sometimes called the infinite duplicate argument, and it follows straightforwardly from the mathematics of infinity, combined with the assumption that the universe is homogeneous on large scales. If you have an infinite number of chances for something to happen, and that something has a non-zero probability, then it happens infinitely many times. Your exact brain state, your exact memories, your exact life history, all of it is repeated infinitely many times throughout infinite space. Now, this doesn't mean you should worry about meeting your doppelganger. These duplicates are so far away, well beyond the cosmological horizon, that you will never interact with them. Light from them will never reach you. They might as well be in a separate universe. But conceptually, it's bizarre. It means that everything that can happen does happen, infinitely many times. Every possible history plays out somewhere. On the other hand, if the universe is finite, then there's a finite amount of stuff, a finite number of galaxies, a finite number of atoms. There might still be an unimaginably large number, but it's not infinite. And that means there are no duplicates. You are unique, the only one, in the entire cosmos. There's something oddly comforting about that, but also isolating. The infinite universe feels abundant, overwhelmingly so, while the finite universe feels contained, manageable, even if it's still vastly larger than anything we can observe. Current observations favor an infinite flat universe, but we can't rule out a finite universe with such slight curvature or such a large topological scale that we simply can't detect it yet. Future observations, especially more precise measurements of the cosmic microwave background and large-scale structure, might tip the balance one way or the other. Or we might remain forever uncertain, limited by the fundamental fact that we can only see out to the cosmological horizon. Anything beyond that is, by definition, unobservable. Now, let's talk about higher dimensions, because this is where things get really speculative but also really interesting. When I said earlier that the universe doesn't expand into a higher dimensional space, I meant that in the context of standard cosmology and general relativity. But there are some theoretical frameworks where extra dimensions do play a role, and it's worth understanding what that means and what it doesn't mean. String theory, for instance, requires the existence of extra spatial dimensions beyond the three we experience. Depending on the version of the theory, there are either 10 or 11 total dimensions, which means 6 or 7 extra spatial dimensions beyond the familiar 3. These extra dimensions are usually assumed to be compactified, meaning they're curled up into tiny shapes so small that we can't detect them. Imagine a garden hose. From far away, it looks like a one-dimensional line. But if you zoom in, you realize it's actually a two-dimensional surface wrapped around in a circle. One dimension extends along the length of the hose, while the other curls around in a tiny loop. String theory proposes that every point in our three-dimensional space is actually a tiny six-dimensional shape, far too small for us to see. These compactified dimensions affect the properties of particles and forces, but they don't provide an external space into which our three-dimensional universe expands. The expansion is still a change in the three large dimensions we experience. The extra dimensions, if they exist, are just along for the ride. But there are other scenarios, particularly in brane world models, where our three-dimensional universe is a membrane, or brane, embedded in a higher dimensional space called the bulk. In these models, our entire universe, all of space and time, is a three-dimensional surface floating in a higher dimensional arena. Gravity can propagate through the bulk, but the other forces and all the matter and energy we interact with are confined to the brane. If this is true, then, in some sense, our universe does exist within a higher dimensional space. But here's the key point. Even in these models, the expansion of our universe is still described as a change in the metric of the brane. Our three-dimensional space is getting larger, but that doesn't necessarily mean the brane is physically moving through the bulk, or that the bulk is providing the space to expand into. The expansion is still an intrinsic property of the brane's geometry. Moreover, these extra dimensions, if they exist, are not spatial dimensions in the way we normally think of them. They don't provide a place you could point to and say, that's where the universe is expanding. They are part of the mathematical structure of reality, but they don't correspond to any intuitive notion of external space. So even when we invoke speculative ideas like string theory and brane worlds, we don't escape the basic conclusion. The expansion of the universe doesn't require it to expand into anything. The geometry is changing, but that change is intrinsic. It's measured from within, not from without. Let me try to bring this all together with a thought experiment. Imagine you're a being that exists in a genuinely two-dimensional universe. Not a surface embedded in three-dimensional space, but an actual two-dimensional space that's all there is. You can move north, south, east, and west. But the concept of up and down doesn't exist. Not because you can't move in that direction, but because that direction isn't part of reality. There is no third dimension. Now, suppose this two-dimensional universe is expanding. Distances between objects are increasing. If you measure the distance to a faraway landmark today, and then measure it again tomorrow, the distance will be larger. What is your universe expanding into? The answer is nothing. There is no third dimension for it to expand into. The expansion is entirely within the two dimensions that exist. The metric of your two-dimensional space is changing. That's all. Our situation is exactly analogous, just one dimension higher. We live in a three-dimensional space, or four-dimensional space-time, and that space is expanding. Distances are increasing, but there's no fourth spatial dimension or fifth dimension of space-time into which we're expanding. The expansion is intrinsic to our three-dimensional space. This is genuinely hard to accept because our intuition is built on experiences in a three-dimensional world. When we see something expand, like a balloon, it's expanding into the room. The room already exists, providing the space for the balloon to occupy. But the universe is not like the balloon. It's like the universe. It's sui generis, one of a kind. There's nothing else to compare it to because it's everything. When we say it's expanding, we mean the internal geometry is evolving according to the Friedmann equations. The scale factor is increasing. That's a complete description. No external space required. No external reference frame needed. Everything is measured and understood from within. Here's another way to think about it that might help. The question, what is the universe expanding into, presupposes that expansion must be expansion into something. It assumes that for something to get bigger, there must be empty space available for it to occupy. But this is only true for objects within space. The universe is not an object within space. It is space. And space can have properties that change over time. The distance between two galaxies is not a fixed, eternal number. It's a dynamical quantity that evolves according to physical laws. General relativity tells us that space-time is a dynamical entity. It can bend, stretch, ripple, even tear under extreme conditions. The expansion of the universe is just one manifestation of this dynamical nature. Space-time is not a static stage on which events unfold. It's a participant, an active player in the cosmos. Its properties change in response to the matter and energy it contains, and those changes feed back into how matter and energy behave. This is the core insight of general relativity, and it's why the question of what the universe expands into is misguided. The question assumes a Newtonian picture where space is a fixed background. But general relativity replaced that picture with one where space-time is dynamical. Space can expand, and it can do so without needing anywhere to expand into. If this still feels unsatisfying, I empathize. It felt unsatisfying to me for a long time. Our brains are not wired to understand this intuitively. We evolved to throw spears and gather berries, not to comprehend the global geometry of space-time. The fact that we can understand it at all, even if only through mathematics, is frankly astonishing. But the mathematics is clear. The universe does not need external space to expand into. The expansion is a change in the metric, the intrinsic geometry of space-time. That's the answer, even if it's not the answer our intuition wants. So, when you find yourself lying awake at night, wondering what's outside the universe, wondering what it's expanding into, remember this. Outside is not a place. It's not a thing. The universe is all of space, and when space expands, it doesn't go anywhere. It just becomes larger, as measured from within. The distances increase, the scale factor grows, and that's the whole story. There's nothing beyond the universe for the same reason there's nothing north of the North Pole. The question itself is based on a misconception about the nature of space and expansion. And once you understand that, the question dissolves. It doesn't need an answer because it was never a coherent question to begin with. Now that we've wrestled with the geometry and topology of the universe, with the question of whether it's finite or infinite, flat or curved, it's time to explore some alternative frameworks for understanding cosmic expansion. Because while the standard Big Bang model with its expanding space has been extraordinarily successful at explaining observations, it's not the only game in town. Cosmologists have proposed various modifications, extensions, and alternatives, each offering a different perspective on what expansion means and where it came from. Some of these ideas are well established and widely accepted. Others are speculative, controversial, and may turn out to be completely wrong. But they're all worth examining because they reveal just how much we still don't understand about the universe at the largest scales. Let's start with inflation, because this is arguably the most important development in cosmology since Hubble's discovery of expansion itself. In 1980, a young physicist named Alan Guth was working on problems related to the early universe when he stumbled onto something remarkable. He realized that if the universe went through a brief period of exponential expansion very early in its history, it would solve several major puzzles that had been plaguing cosmologists. The first of these is the horizon problem. When we look at the cosmic microwave background, we see that it has almost exactly the same temperature in every direction. The variations are only about 1 part in 100,000. This uniformity is puzzling, because regions of the sky that are separated by more than about 2 degrees never had time to be in causal contact with each other in the standard Big Bang model. Light from one region couldn't have reached the other region by the time the CMB was emitted, about 380,000 years after the Big Bang. So, how did these causally disconnected regions end up at the same temperature? It's like walking into a room and finding that every molecule of air is at exactly the same temperature, even though the molecules at opposite ends of the room have never interacted. It shouldn't happen unless something caused them to equilibrate before they became disconnected. Guth's inflation provides that something. If the universe underwent a period of exponential expansion very early, around 10 to the minus 36 seconds after the Big Bang, then regions that are now widely separated were once close together, in causal contact. They had time to reach thermal equilibrium. Then inflation stretched space by an enormous factor, something like 10 to the 26 or more, carrying these regions far apart. By the time normal expansion took over, they were causally disconnected, but they retained their uniform temperature from the pre-inflation era. Problem solved. The second problem inflation solves is the flatness problem, which I mentioned earlier. The universe today appears to be extremely flat, with curvature close to zero. But flatness is unstable. If the universe had even a tiny amount of curvature early on, that curvature would have grown rapidly as the universe expanded. For the universe to be as flat as it is today, it must have been flat to an absurd degree of precision in the early universe. Something like 1 part in 10 to the 60 just 1 second after the Big Bang. Why would the initial conditions be so finely tuned? Inflation provides an answer. Exponential expansion stretches space so much that any initial curvature gets flattened out, like blowing up a balloon until its surface looks perfectly flat on small scales. Even if the universe started with significant curvature, inflation would have driven it to flatness. This is why we observe a flat universe today. Not because the initial conditions were special, but because inflation made it flat regardless of how it started. The third problem is the monopole problem, which is a bit more technical. Various theories in particle physics predict that the early universe should have produced vast numbers of magnetic monopoles, hypothetical particles that are like isolated north or south magnetic poles. These monopoles should be incredibly massive and stable, and if they were produced in the expected quantities, they'd dominate the mass of the universe. We'd see them everywhere, but we've never detected a single one. Inflation solves this by diluting the monopoles. If monopoles were produced before inflation, the exponential expansion would have spread them out so much that their density became negligible. There might be a handful of monopoles scattered across the entire observable universe, far too rare to detect. So, inflation explains the uniformity of the CMB, the flatness of space, and the absence of monopoles. It's an elegant solution to multiple problems. But what exactly is inflation? What drove this exponential expansion? The answer is a hypothetical field called the inflaton. In physics, fields are entities that permeate space and have a value at every point. The electromagnetic field is a familiar example. Temperature is another, though it's not a fundamental field. The inflaton is a scalar field, meaning it has a magnitude but no direction, and it's associated with a potential energy. In the very early universe, the inflaton field was sitting at a high energy state, far from its minimum. This potential energy acted like a cosmological constant, driving exponential expansion. As the field slowly rolled down toward its minimum, the universe expanded exponentially. Then, when the inflaton reached the minimum of its potential, it oscillated and decayed, converting its energy into ordinary particles and radiation. This process, called reheating, populated the universe with the matter and energy we see today. Inflation ended, and normal expansion took over. Now, here's where things get wild. Inflation doesn't just solve problems, it also makes predictions, and some of those predictions have been confirmed. Inflation predicts that quantum fluctuations in the inflaton field would have been stretched to cosmic scales, creating tiny variations in the density of matter. These density fluctuations are the seeds that grew into galaxies and large-scale structure. When we look at the cosmic microwave background, we see exactly the kind of fluctuations inflation predicts. The pattern, the spectrum, the statistics, they all match. This is one of the greatest successes of modern cosmology. But inflation also leads to some bizarre implications. In most versions of inflation, once it starts, it never completely stops. In some regions of space, the inflaton field reaches its minimum and inflation ends. But in other regions, quantum fluctuations can push the field back up and inflation continues. And in some of those regions it continues forever, spawning more and more regions where inflation ends and others where it continues. This is called eternal inflation, and it leads to a multiverse, an infinite collection of bubble universes, each with potentially different physical laws, different constants of nature, different numbers of dimensions. Our universe is just one bubble in an eternally inflating multiverse. In some bubbles, the cosmological constant is much larger than in ours, and those universes expand so fast that galaxies never form. In others, the constants are different, and atoms can't exist. We live in a bubble where the conditions happen to be right for complexity, structure, and life. This is often invoked as an explanation for why our universe seems so finely tuned. It's not that the universe was designed for us, it's that there are countless universes with different properties, and we necessarily find ourselves in one where life is possible. This is the anthropic principle, and it's deeply controversial. Some physicists love it. Others hate it because it seems to abandon the goal of explaining why the constants of nature have the values they do. If every possible value occurs somewhere in the multiverse, then asking why our universe has these particular values is like asking why you were born in this particular city. It's just where you happen to be. Now, does eternal inflation mean the universe is expanding into something? Not really. Each bubble universe is still expanding within its own space, and that expansion is intrinsic. The multiverse as a whole might be described as existing in some abstract mathematical space, but that's not a physical space you could travel through. The different bubble universes are causally disconnected from each other. You can't leave our bubble and visit another one. They're not places in space. They're separate space-time regions that don't interact. So, even in the multiverse scenario, the answer to what the universe is expanding into remains the same: nothing. Each bubble expands intrinsically, and the existence of other bubbles doesn't change that. But inflation isn't the only game in town. There are alternative cosmologies that challenge or modify the standard picture. One of the most intriguing is the cyclic or bouncing cosmology. The idea here is that the universe doesn't have a singular beginning at the Big Bang. Instead, it goes through cycles of expansion and contraction, bouncing back and forth for eternity. In one version, proposed by physicists Paul Steinhardt and Neil Turok, the universe undergoes a Big Bang, expands for trillions of years, then contracts in a big crunch, only to bounce and expand again in a new Big Bang. Each cycle erases most of the information from the previous cycle, but certain features, like the flatness and uniformity of space, are preserved. The cyclic model was inspired partly by dissatisfaction with eternal inflation and the multiverse. Steinhardt and Turok wanted a model that explained the observed properties of the universe without invoking an infinite ensemble of unobservable universes. Their model involves extra dimensions and brain worlds, where our universe is a three-dimensional brain colliding with another brain in a higher dimensional space. The collision is what we perceive as the Big Bang. In another version, the universe bounces at a very high but finite density, avoiding the singularity of the classical Big Bang. This bounce is made possible by quantum effects that become important when the universe is extremely small and dense. These quantum corrections to general relativity prevent the collapse from reaching infinite density, and instead, the universe rebounds into an expanding phase. Bouncing cosmologies are appealing because they avoid the problem of the initial singularity. In the standard Big Bang model, if you run the clock backward, you reach a point where the density and temperature become infinite. General relativity breaks down. We can't describe what happens at the singularity, and we certainly can't say anything about what came before. A bouncing cosmology sidesteps this by saying there is no singularity. The universe contracts to a very small size, then bounces. You can keep running the clock backward through earlier and earlier cycles, potentially forever. There's no beginning, just an eternal sequence of expansions and contractions. But bouncing cosmologies have their own challenges. For one thing, the second law of thermodynamics says that entropy, the amount of disorder, always increases. If the universe has been cycling forever, entropy should be infinite by now, and we should observe a universe in thermal equilibrium, with no structure, no stars, no galaxies. Just a uniform sea of radiation. The fact that we see structure suggests the universe hasn't been cycling forever, or there's some mechanism that resets entropy during each bounce. Neither option is particularly satisfying. Another alternative is the idea that the universe emerged from a quantum state, with no classical beginning at all. This is the realm of quantum cosmology, where we try to apply the principles of quantum mechanics to the universe as a whole. In quantum mechanics, particles don't have definite positions and velocities until you measure them. They exist in a superposition of all possible states, described by a wave function. Quantum cosmology applies the same idea to the universe. The universe doesn't have a definite size or shape or history. Instead, it exists as a wave function, a superposition of all possible universes. One of the most famous proposals along these lines is the Hartley-Hawking no-boundary proposal, developed by James Hartley and Stephen Hawking in the 1980s. They suggested that the universe has no boundary in time. The Big Bang is not a moment where time begins. Instead, as you go back in time toward the Big Bang, time becomes more and more like space, and the distinction between space and time blurs. Imagine the surface of the Earth. If you ask what's south of the South Pole, the question doesn't make sense because the South Pole is the southernmost point. there's nothing beyond it, not because there's a wall, but because the direction south ceases to be meaningful at the pole. Hartley and Hawking proposed that time works the same way near the Big Bang. If you go back far enough, time smoothly transitions into a space-like dimension, and the question of what happened before the Big Bang becomes meaningless. There is no before. The universe is finite in time, but has no boundary. This is a beautiful idea, and it neatly avoids the problem of the initial singularity. But it's also extraordinarily difficult to test. The Hartley-Hawking proposal makes predictions about the wave function of the universe, which in turn affects the probability of observing different kinds of universes. But calculating these probabilities requires solving the Wheeler-DeWitt equation, the quantum equation for the universe, and that's notoriously difficult. Moreover, we only have one universe to observe, so even if we calculate that certain features are more probable, we can't repeat the experiment and check. Quantum cosmology is fascinating and profound, but it's also highly speculative. Another quantum approach is loop quantum cosmology, which comes from loop quantum gravity, an attempt to quantize gravity without relying on extra dimensions or strings. In loop quantum cosmology, space is made up of discrete, quantized units, tiny loops of space that can't be subdivided further. When you try to compress the universe down to the Planck scale, about 10 to the minus 35 meters, quantum effects kick in and prevent further collapse. The universe bounces, transitioning from a contracting phase to an expanding phase. This provides a natural mechanism for a big bounce, resolving the singularity problem. Loop quantum cosmology makes testable predictions about the cosmic microwave background, and astronomers are actively searching for these signatures. So far, the data are consistent with both standard inflation and loop quantum cosmology, so we can't yet distinguish between them. But future observations might tip the balance. Then there are even more speculative ideas, like the possibility that space-time itself is emergent, not fundamental. In this view, space-time is not the basic fabric of reality, but rather something that arises from more fundamental entities, perhaps bits of information or quantum entanglement, or something else entirely. This is the domain of theories like string theory, loop quantum gravity, and other approaches to quantum gravity. In string theory, the fundamental objects are not particles, but tiny vibrating strings. Different vibration modes correspond to different particles, including the graviton, the hypothetical particle that mediates gravity. String theory requires extra dimensions, as I mentioned earlier, and it predicts a vast landscape of possible vacuum states, each corresponding to a different universe with different laws of physics. The landscape is so large, something like 10 to the 500 different possibilities, that it's hard to make definite predictions. This is sometimes called the string theory landscape problem. With so many possibilities, how do we know which one describes our universe? Some physicists argue that all of these possibilities are realized somewhere in the multiverse, bringing us back to the anthropic principle. Others are working on ways to narrow down the landscape, finding principles that select a unique or small set of vacuum states. Loop quantum gravity takes a different approach. It quantizes spacetime itself, treating it as a network of discrete loops. Space is not continuous but made up of tiny, quantized chunks. Time, too, might be quantized, ticking forward in discrete steps rather than flowing smoothly. If space-time is emergent, then the question of what the universe is expanding into becomes even more abstract. The expansion is not something happening in space, but rather a change in the relationships between fundamental entities. Space itself is an emergent concept, a useful approximation at large scales, but not a part of the fundamental description of reality. In this view, asking what the universe expands into is like asking what temperature is made of. Temperature is an emergent property of large collections of particles. It's not a fundamental thing. Similarly, space might be an emergent property of quantum degrees of freedom, and expansion might be an emergent phenomenon that describes how these degrees of freedom evolve. This is all highly speculative, but it points to a deeper truth. Our concepts of space, time, and expansion are ultimately human constructs, ways of making sense of the universe at the scales we can observe. At the deepest levels, reality might be described in completely different terms, using mathematics that doesn't directly correspond to our intuitive notions of space and time. There's also the holographic principle, which suggests that all the information in a volume of space can be encoded on the boundary of that volume, like a hologram. This idea comes from studying black holes, where physicists realized that the entropy, the amount of information, is proportional to the surface area of the black hole's event horizon, not its volume. This seems to suggest that the three-dimensional interior of a black hole is somehow encoded in its two-dimensional surface. The holographic principle extends this idea to the universe as a whole. Perhaps our three-dimensional universe is actually a hologram, a projection from information encoded on a two-dimensional surface far away, perhaps at the cosmological horizon. If this is true, then the expansion of the universe might be reinterpreted as a change in the encoding on the boundary. The volume increases, but the fundamental description is in terms of the boundary, not the interior. This is a radical reconception of what space is and what it means for it to expand. Again, this is speculative, but it's grounded in serious theoretical work, particularly in the context of string theory and the ADS-CFT correspondence, a mathematical duality that relates a theory of gravity in a higher dimensional space to a theory without gravity in a lower dimensional space. If the universe is holographic, then space is not fundamental. It's an emergent description of something more basic, and the expansion of space is an emergent phenomenon, a way of describing changes in the underlying holographic encoding. Now, I realize that all of this might sound like we're getting farther and farther from answering the original question. But that's actually the point. The more we learn about the universe at the deepest levels, the more we realize that our everyday concepts of space and expansion are approximations. They work beautifully at the scales we observe, but they break down when we push to the very large, the very small, or the very early universe. The question of what the universe is expanding into assumes that space is a fundamental, well-defined thing with clear properties. But modern physics suggests that space might be emergent, approximate, or even an illusion in some sense. And if that's the case, then the question dissolves. There's no into because space itself is not what we thought it was. Let me try to bring some of this back down to Earth, or at least to something more concrete. The standard cosmological model, the lambda CDM model, describes the universe as composed of ordinary matter, and dark energy. Lambda refers to the cosmological constant, Einstein's old fudge factor, which we now interpret as dark energy. CDM stands for cold, dark matter, a hypothetical form of matter that doesn't interact with light but exerts gravitational influence. This model fits the data remarkably well. It explains the cosmic microwave background, the large-scale structure of galaxies, the acceleration of the expansion, and many other observations. But it's also deeply puzzling because we don't know what dark matter or dark energy actually are. Dark matter makes up about 27% of the universe's energy content, and we've never directly detected a dark matter particle. We infer its existence from gravitational effects, like the rotation curves of galaxies and the bending of light around massive clusters. But despite decades of searching, we haven't found the particle responsible. It might be a new kind of particle predicted by extensions to the standard model of particle physics. Or it might be something else entirely, like primordial black holes or modifications to gravity. Dark energy is even more mysterious. It makes up about 68% of the universe, and we have no idea what it is. The simplest explanation is that it's the energy of empty space, the vacuum energy. Quantum field theory predicts that even empty space should have energy due to the constant creation and annihilation of virtual particles. But when we calculate the expected value of this vacuum energy, we get a number that's about 10 to the 120 times larger than what we observe. This is the cosmological constant problem, sometimes called the worst prediction in the history of physics. The observed value of dark energy is incredibly small, but not zero. Why? We don't know. Some physicists think the vacuum energy is exactly zero for some unknown reason, and dark energy is something else, a dynamical field called quintessence that changes over time. Others invoke the anthropic principle, arguing that in a multiverse, only universes with a very small cosmological constant can form galaxies and stars and life, so we necessarily observe a small value. Neither explanation is satisfying, and the cosmological constant problem remains one of the biggest unsolved puzzles in physics. But whatever dark energy is, it's driving the accelerated expansion of the universe. And this has profound implications for the future. As the universe expands, matter becomes more and more dilute. But dark energy, if it's truly a cosmological constant, doesn't dilute. It has the same density everywhere and at all times. So as the universe expands, dark energy comes to dominate more and more. Eventually, the universe will be expanding so fast that galaxies outside our local group will be receding faster than light. They'll cross the cosmological horizon and disappear from view. Stars will burn out, and no new stars will form because all the gas will be too dilute. The universe will become cold, dark, and empty. This is sometimes called the heat death or big freeze, and it's the most likely fate of our universe given current observations. But there are other possibilities. If dark energy is not constant but increases over time, the expansion could accelerate so much that it rips apart galaxies, stars, planets, and eventually atoms. This is the Big Rip. On the other hand, if dark energy decreases or reverses, the expansion could slow, stop, and reverse, leading to a big crunch where the universe collapses back in on itself. We don't know which of these fates awaits us because we don't understand dark energy. But all of them are consistent with the idea that the universe is not expanding into anything. The expansion is intrinsic, a change in the scale factor, and that change will continue, accelerate, or reverse depending on the dynamics of dark energy. No external space is involved. We've journeyed through the history of cosmic expansion, grappled with what expansion really means, explored the geometry and topology of space, and surveyed alternative cosmological frameworks. Now it's time to bring everything together and confront the deeper implications of what we've learned. Because the question of what the universe is expanding into isn't just a technical puzzle for physicists. It's a profound challenge to how we understand reality itself, and the answer, or lack thereof, forces us to reconsider some of our most basic assumptions about existence. Let's start with the discovery that changed everything about our understanding of the universe's fate. In 1998, two independent teams of astronomers were studying distant supernovae, specifically type Ia supernovae, those exploding white dwarf stars I mentioned earlier. These supernovae are excellent standard candles because they all explode with roughly the same intrinsic brightness. By measuring how bright they appear and comparing that to how bright they should be, you can calculate their distance. Both teams were trying to measure how much the expansion of the universe was slowing down. Everyone expected the expansion to be decelerating because gravity pulls everything together. The only question was how much? Would the universe eventually stop expanding and collapse back in a big crunch? Or would it expand forever, gradually slowing but never quite stopping? The teams measured supernovae at various distances, looking back billions of years into cosmic history. And what they found shocked everyone. The expansion wasn't slowing down, it was speeding up. Distant supernovae appeared fainter than expected, which meant they were farther away than they should be if the universe had been expanding at a constant or decelerating rate. Somehow, the expansion had accelerated. This made no sense. There's no known form of matter or radiation that could cause the universe to accelerate. Gravity is attractive. It should slow expansion, not speed it up. The only way to get acceleration is if there's some form of energy with negative pressure, a sort of anti-gravity that pushes space apart rather than pulling it together. And the only candidate anyone had ever proposed for such a thing was Einstein's cosmological constant. Suddenly, Einstein's biggest blunder wasn't a blunder at all. The cosmological constant, which Einstein had introduced to keep the universe static and then discarded when Hubble discovered expansion, was back. Except now we call it dark energy, and it's the dominant component of the universe. The discovery won the Nobel Prize in Physics in 2011, and it fundamentally changed our understanding of cosmology. But it also created a mystery that remains unsolved to this day. Dark energy makes up about 68% of the total energy content of the universe. Dark matter accounts for about 27%. And ordinary matter, the stuff that makes up stars and planets and you and me, is a mere 5%. We live in a universe where 95% of the content is completely unknown. We can measure the effects of dark energy. We can see that it causes the expansion to accelerate, but we have no idea what it actually is. The simplest explanation is that it's the vacuum energy, the energy of empty space itself. Quantum field theory tells us that the vacuum isn't really empty. It's seething with virtual particles that pop in and out of existence. These quantum fluctuations should contribute energy to the vacuum, and that energy should act like a cosmological constant, causing space to expand. So far, so good. But when physicists try to calculate how much vacuum energy there should be, they get a catastrophically wrong answer. Depending on how you do the calculation, the predicted value of the vacuum energy is either 10 to the 120 times larger than observed, or at the very least 10 to the 55 times larger. These are not small discrepancies. This is the cosmological constant problem, and it's arguably the biggest unsolved problem in fundamental physics. Why is the observed value of dark energy so incredibly small, yet not exactly zero? Nobody knows. Some physicists think there must be some mechanism, some symmetry or principle we don't yet understand, that forces the vacuum energy to be exactly zero or nearly zero. Others invoke the anthropic principle and the multiverse. If there are countless universes with different values of the cosmological constant, then we necessarily find ourselves in one where the value is small enough to allow galaxies and stars and life to form. In universes with much larger cosmological constants, the expansion would be so rapid that matter could never clump together. No galaxies, no stars, no planets, no observers. So, of course, we observe a small cosmological constant. We couldn't exist otherwise. This anthropic explanation is unsatisfying to many physicists because it seems to give up on explaining why the constants of nature have the values they do. But others argue it's the only explanation that makes sense given the landscape of possibilities in string theory and eternal inflation. The debate continues, and we're no closer to a resolution. What we do know is that dark energy is causing the universe to expand faster and faster, and this has profound implications for the long-term future of the cosmos. As the universe expands and accelerates, galaxies that are currently observable will eventually cross the cosmological horizon and disappear from view. Their light will be stretched to longer and longer wavelengths, redshifted into the infrared, then radio waves, and eventually the wavelength will be longer than the size of the observable universe. They'll fade from existence, at least from our perspective. In the very distant future, trillions of years from now, an observer in our galaxy would look out and see almost nothing. The cosmic microwave background would be redshifted to such low energies that it would be undetectable. All the distant galaxies would have vanished beyond the horizon. The only visible objects would be the galaxies in our local group, a small cluster of a few dozen galaxies bound together by gravity. These galaxies will eventually merge into a single massive galaxy, and beyond that, nothing. No evidence of the Big Bang, no distant galaxies, no expanding universe. A future cosmologist looking out from this lone galaxy surrounded by darkness would have no way to discover that the universe had a beginning or that it's expanding. All the evidence we've used to uncover the history of the cosmos would be gone, erased by the relentless expansion. This is sometimes called the cosmic dark age, though it's not really an age so much as a permanent state. And it raises a disturbing question. What if we're already in that situation? What if there's cosmological evidence that's already been stretched beyond our horizon? Information about the universe that we can never access because it's too far away. We might be missing crucial pieces of the puzzle without even knowing it. In fact, we almost certainly are. The observable universe is just a tiny patch of the total universe. And beyond our horizon, there could be regions with completely different properties, different values of the constants, different physical laws, structures we can't imagine. We'll never know because we can't see them. This brings us back to a recurring theme. The universe we can observe is not the entire universe. It's just the part that's close enough for light to have reached us in the 13.8 billion years since the Big Bang. The full universe might be vastly, incomprehensibly larger. And when we talk about that universe expanding, we're describing something much grander than what we can see. So, what is it expanding into? The answer remains the same. Nothing. The expansion is intrinsic. But now we can appreciate just how limited our perspective is. We're like inhabitants of a small island, describing the properties of the entire ocean based on what we can see from the shore. We might be mostly right, or we might be missing something fundamental. Let's talk about the ultimate fate of the universe because this connects directly to the nature of expansion. If dark energy remains constant, which is what current observations suggest, then the universe will continue to expand forever, accelerating without limit. This scenario is called the Big Freeze, or heat death. The universe will become increasingly cold, dark, and empty. Stars will exhaust their fuel and die. No new stars will form because the gas needed to make them will be too diffuse. Galaxies will fade as their stars burn out. Eventually, even black holes will evaporate through Hawking radiation, a quantum process that causes black holes to slowly lose mass. The timescale for this is absurdly long. A black hole with the mass of the Sun would take 10 to the 67 years to evaporate. A supermassive black hole could take 10 to the 100 years or more. But given infinite time, even these will eventually disappear. What's left is a universe filled with nothing but photons, neutrinos, and a few stray particles, all stretched to incredibly long wavelengths by the expansion. The temperature approaches absolute zero. No structure, no complexity, no life, just emptiness. This might sound depressing, but it's worth noting that this is an almost unimaginably distant future. The universe is currently 13.8 billion years old. The last stars won't form for at least another trillion years. Black holes will linger for countless eons beyond that. By the time the universe reaches its final cold state, the current epoch, the age of stars and galaxies, will be a vanishingly brief moment, a fleeting instant in the infinite expanse of cosmic history. But there are other possibilities. If dark energy is not constant, but instead increases over time, the expansion could accelerate so much that it overcomes not just the gravitational binding of galaxies and stars, but eventually even the forces holding atoms together. This is the Big Rip scenario. In this scenario, the expansion becomes so violent that everything gets torn apart. First, galaxy clusters are disrupted as the space between galaxies expands faster than gravity can hold them together. Then, individual galaxies are shredded, then solar systems, then planets. Eventually, even atoms are ripped apart as the expansion of space overwhelms the electromagnetic forces binding electrons to nuclei. The universe ends in a cataclysmic disintegration, where every structure, down to the subatomic level, is destroyed. The timescale for the Big Rip depends on how quickly dark energy increases, but some models suggest it could happen in as little as 20 billion years. We'd see the warning signs. Distant galaxies would start disappearing faster than expected. The cosmic microwave background would show unusual distortions, and eventually, we'd see nearby structures beginning to come apart. Of course, by then, it would be far too late to do anything about it. On the other hand, if dark energy decreases or reverses, the expansion could slow down, stop, and eventually reverse. The universe would begin to contract. Galaxies would start moving toward each other instead of away, and everything would collapse back into a big crunch. This is essentially the time reverse of the Big Bang. As the universe contracts, it gets denser and hotter. Galaxies collide and merge. Stars are torn apart by tidal forces. Eventually, the entire universe is compressed into a hot, dense state similar to the early universe, and possibly into a singularity where density and temperature become infinite, and the laws of physics break down. The Big Crunch was once thought to be the most likely fate of the universe, back before the discovery of dark energy. If the universe contained enough matter, gravity would eventually halt the expansion and pull everything back together. But now we know that dark energy is dominant and causing acceleration, so the Big Crunch seems unlikely. unless dark energy changes its properties in the future, which is possible but not predicted by any well-established theory. There's also the possibility of a cyclic universe, where the big crunch is followed by a big bounce and a new cycle of expansion. As I mentioned in the previous section, cyclic models avoid the problem of the initial singularity by proposing that the universe has no beginning, just an eternal sequence of expansions and contractions. Each cycle could last trillions of years, with the universe expanding, slowing, contracting, bouncing, and expanding again. Information from previous cycles might be partially preserved or entirely erased. We could be living in cycle number 10, or 10 billion, or infinity. We have no way to know. Cyclic models are speculative and face significant theoretical challenges, particularly with entropy and the second law of thermodynamics. But they remain an active area of research, and they offer a very different perspective on what expansion means. Instead of a one-time event leading to eternal growth or a final collapse, expansion is just one phase in an endless cosmic rhythm. So, which fate awaits our universe? We don't know. It depends entirely on the nature of dark energy, and we don't understand dark energy. Current observations favor the big freeze, eternal expansion with increasing coldness and emptiness. But we can't rule out the big rip or more exotic scenarios. The universe might have surprises in store. Let's step back and consider the philosophical implications of everything we've discussed. The question of what the universe is expanding into is deeply connected to how we think about existence itself. For most of human history, people thought of the universe as a container. There was space, and things existed within that space. Space was the stage, and matter and energy were the actors. The stage itself was passive, unchanging, absolute. Isaac Newton formalized this view with his concept of absolute space, a fixed three-dimensional grid that existed independently of the matter and energy it contained. Time, too, was absolute, flowing uniformly everywhere. This Newtonian picture dominated physics for 2 centuries, and it's still how most people intuitively think about the world. But Einstein's general relativity shattered this picture. Space and time are not fixed and absolute. They're dynamical. They're influenced by matter and energy, and they influence matter and energy in turn. Space-time is not a passive container, but an active participant in the cosmos. This is the key insight that makes cosmic expansion possible without needing external space. The expansion is a change in space-time itself, and this leads to a profound shift in how we understand reality. Space is not a thing. It's a relationship. It's the web of distances and intervals between events and objects. When we say space is expanding, we're saying those relationships are changing. The web is stretching. But the web doesn't exist inside anything. It is the fundamental structure. There is no external reference frame, no higher-level space in which our space is embedded. This is genuinely hard to accept because our intuitions are built on experiences within space. We see objects expand into surrounding space. A city grows into the countryside. A balloon inflates into the room. So, when we hear that the universe is expanding, we instinctively imagine it expanding into something. But the universe is not an object within space. It is space. And recognizing this requires a shift in thinking that doesn't come naturally. It's similar to the shift required to understand that the Earth has no edge. For most of history, people assumed the Earth was flat and must have an edge somewhere. You could walk far enough and eventually fall off. When it was discovered that the Earth is round, it took time for people to accept that you could travel forever and never reach an edge, not because the Earth is infinite, but because it curves back on itself. The surface of the Earth is finite but unbounded. Our universe might be the same way, or it might be infinite. Either way, there's no edge and there's no outside. The concept of outside simply doesn't apply. This brings us to a deeper question. If the universe is all that exists, and it doesn't need external space to expand into, then what does it even mean for something to exist? Existence, in our everyday experience, always means existing somewhere, at some location in space. But the universe doesn't exist in space. It is space. So, in what sense does it exist? This is where physics blurs into philosophy, and different people will have different answers. Some philosophers argue that existence is a brute fact, something that doesn't require explanation. The universe exists because it exists. Asking why or how is like asking what caused the number 2. Numbers don't have causes, they just are. Maybe the universe is the same. Others argue that existence requires grounding in something more fundamental. Maybe the universe exists because it's a solution to some mathematical equation, a logical necessity. Or maybe it exists because some entity or principle brings it into being. But these answers just push the question back. What grounds the equation? What grounds the entity? You either accept an infinite regress, or you accept that something exists without further explanation. Cosmology can't resolve these questions. It can describe how the universe behaves, how it evolves, what its structure is. But it can't explain why there is something rather than nothing. That's beyond the scope of science. What cosmology can do is reveal just how strange and counterintuitive the universe really is. It's not the cozy, static, human-scaled cosmos of ancient imagination. It's a vast, expanding, evolving structure governed by laws that often defy common sense. And the expansion into nothing is just one of many features that challenges our intuitions. Consider the Big Bang. It's often described as an explosion, a burst of matter and energy from a point. But that's not right. The Big Bang was not an event in space. It was the beginning of space itself, or at least of the current expansion phase. Every point in space was part of the Big Bang. There was no center, no location where it happened. It happened everywhere, simultaneously. If the universe is infinite, then the Big Bang was an infinite expanse at infinite density and temperature, which then expanded and cooled. If the universe is finite, then the Big Bang was a finite but very small and very dense state that expanded. Either way, asking where the Big Bang happened is like asking where the surface of the Earth begins. It doesn't begin anywhere. It's a closed loop, or, in the case of the Big Bang, a moment in time that applies to all of space. This is part of why the question of what the universe is expanding into is so slippery. It's based on intuitions that don't apply to the cosmos as a whole. We're trying to use concepts that work for objects within the universe and apply them to the universe itself. But the universe doesn't follow the same rules as the objects it contains. Let's return to that analogy I used earlier, the question of what's north of the North Pole. It seems like a reasonable question. North is a direction, and you can keep going north from anywhere on Earth. So surely there must be something north of the North Pole. But once you understand the geometry of the Earth, you realize the question is based on a misunderstanding. North is defined as the direction toward the North Pole. At the pole itself, every direction is south. There is no north of the North Pole, not because there's a wall or barrier, but because the concept of north ceases to be meaningful at that location. The question of what the universe is expanding into is similar. Expansion is defined as an increase in distances within space. Outside of space is not a place. It's not a direction you can point to. The concept simply doesn't apply. And once you understand the geometry and dynamics of space-time, you realize the question is malformed. It's asking for something that doesn't exist and doesn't need to exist for expansion to occur. Now, I realize this might still feel unsatisfying. You might intellectually accept the explanation, but still have this nagging feeling that there must be something more, some deeper answer. And that's okay. That feeling is a sign that you're grappling with ideas that are genuinely difficult and counterintuitive. Even physicists who work on these problems every day sometimes struggle with the implications. The key is to recognize that our intuitions are tools, heuristics that evolved to help us navigate the world at human scales. They're incredibly useful for everyday life. But they're not infallible. When we push into extreme regimes, the very large or the very small or the very fast, our intuitions often fail us. Quantum mechanics doesn't make intuitive sense. Relativity doesn't make intuitive sense. And cosmology, the study of the universe at the largest scales, definitely doesn't make intuitive sense. But that doesn't mean these theories are wrong. It means the universe is stranger than our intuitions can accommodate. And that's actually one of the most exciting things about science. It reveals a reality that's far richer and more surprising than anything we could have imagined based on everyday experience alone. So let's consider what current research is telling us and where cosmology is headed. The discovery of dark energy in 1998 opened up a new era of precision cosmology. We've made enormous strides in measuring the properties of the universe. We know its age to within 1%. We know its composition, at least in terms of percentages, even if we don't know what most of that composition actually is. We know the rate of expansion, the Hubble constant, although as I mentioned earlier, there's a troubling discrepancy between different measurement methods. This Hubble tension might be telling us that something is wrong with our model. Maybe dark energy isn't constant. Maybe it evolves over time. Maybe there are additional components we haven't accounted for, like a new type of particle or field. Or maybe general relativity needs to be modified at very large scales. We don't know, but it's one of the most exciting open questions in cosmology today. Future observations will help narrow down the possibilities. The James Webb Space Telescope is already providing unprecedented views of the early universe, looking back to when the first galaxies were forming. These observations constrain models of cosmic inflation and the formation of large-scale structure. Upcoming experiments like the Vera Rubin Observatory and the Euclid space mission will map billions of galaxies, measuring their distances and redshifts with exquisite precision. This will allow us to trace the history of cosmic expansion in much greater detail and potentially resolve the Hubble tension. Gravitational wave observatories like LIGO, Virgo, and the future LISA mission will detect ripples in space-time from colliding black holes, neutron stars, and possibly even from the inflationary era itself. These gravitational waves carry information about the universe that's completely independent of electromagnetic observations, opening a new window on the cosmos. And there are efforts to detect the 21-centimeter line of neutral hydrogen from the early universe, before the first stars formed. This would allow us to probe the so-called Dark Ages, a period about which we currently know almost nothing. All of these observations will refine our understanding of cosmic expansion and might reveal new physics. But they're unlikely to change the fundamental answer to the question we've been exploring. The universe doesn't expand into anything. That's a feature, not a bug, of how space-time works. What future observations will do is help us understand why the expansion is accelerating, what dark energy is, whether the universe will expand forever or eventually collapse, and what happened in the earliest moments after the Big Bang. These are profound questions, and answering them will be one of the great achievements of 21st century science. Let me close with a reflection on what all of this means. The question of what the universe is expanding into is, in some ways, the perfect question. It sounds simple. It seems like it should have a straightforward answer. But digging into it reveals layers of complexity and forces us to confront the limits of our intuition. The answer, that the universe isn't expanding into anything, that expansion is an intrinsic change in the geometry of space, is both elegant and deeply counterintuitive. It's elegant because it doesn't require any extra ingredients. No higher dimensional space, no external container, no mysterious ether. Just space-time behaving according to the equations of general relativity. But it's counterintuitive because it violates our everyday experience of how expansion works. And that tension between mathematical elegance and intuitive discomfort is characteristic of modern physics. We have learned that the universe doesn't care about our intuitions. It operates according to principles that are often at odds with how we expect things to work. Quantum mechanics tells us that particles can be in two places at once, that observation affects reality, that the universe is fundamentally probabilistic rather than deterministic. Relativity tells us that time is not absolute, that it flows differently for different observers, that space and time are intertwined. And cosmology tells us that the universe is expanding without expanding into anything, that space itself is dynamic, that the cosmos is far stranger and more majestic than we imagined. But here's the thing. Even though these ideas are counterintuitive, they're not beyond our grasp. Humans, through the power of mathematics and careful observation, have been able to uncover these truths. We can't visualize four-dimensional space-time, or imagine what it's like for space to expand intrinsically. But we can describe it mathematically, make predictions, test those predictions, and confirm that our descriptions match reality. That's astonishing. We are a species that evolved on the savannas of Africa, adapted to throw rocks and recognize faces and avoid predators. We have no business understanding the large-scale structure of the universe or the behavior of subatomic particles. And yet, somehow, we do. Not perfectly, not completely, but well enough to send spacecraft to the edge of the solar system, to detect gravitational waves from black holes billions of light-years away, to peer back in time to the earliest moments of cosmic history. That's the triumph of science. It allows us to transcend our limitations and glimpse the underlying structure of reality. So, when you find yourself puzzled by the expansion of the universe, when you struggle to understand how something can grow without growing into something else, remember that you're in good company. These questions have puzzled the greatest minds in physics. Einstein himself resisted the idea of an expanding universe at first. Even today, cosmologists debate the interpretation and implications of expansion. But through a combination of rigorous mathematics, careful observation, and yes, a willingness to accept conclusions that defy intuition, we've arrived at an answer. The universe is expanding. Distances between galaxies are increasing. the scale factor is growing. And all of this happens without the universe expanding into any external space, because there is no external space. Space is the thing itself, and it's changing. That's the answer. It's not the answer our intuition wants, but it's the answer the universe gives us. And in the end, that's what matters. Not whether reality conforms to our expectations, but whether we can set aside those expectations and see the universe as it truly is. Strange, vast, expanding, and utterly indifferent to our desire for simple explanations. That's cosmology. That's the universe. And understanding it, even imperfectly, even through the lens of mathematics that we can barely visualize, is one of the greatest achievements of human thought.